Alright, last bit to cover on this compound events, counting outcomes stuff. Here we have an example. The tree diagram shows the possible outcomes of choosing one card and then setting it aside and choosing a second card. So is this independent or dependent? This is dependent. So looking at the tree diagram, what is the probability of at least one fish or one apple? So we would have all four of these combinations because that starts with fish. We would have all four of these combinations because that starts with apple. Then we would have the fish and apple, fish and apple, fish and apple from down here. So that is 4, 2, 4, 2, 2. We'll just add them all up to see what the total number of combinations would be. 4 plus 2 is 6, plus 4 is 10, plus 2 plus 2. That would be 14 different combinations having a fish or apple. Out of, we would have 1, 2, 3, 4 times 5 out of 20 different combinations we could make. So I would simplify that to be 7, it'll write 7 out of 10. Okay? Alright, it is your turn to pick a geography fair partner in country at random. Using an organized list, a table, or a tree diagram, we're going to find the probability of choosing your best friend Miguel and your favorite country, Greece. So Miguel and Greece. Well, how many choices do I have in the box for the name? I have 1, 2, 3, 4, 5. There are 5 names. And then how many countries? I have 1, 2, 3 countries. So let's multiply. 5 times 3, there are 15 different combinations that I could make. But how many of those combinations would have Miguel and Greece? Just one of them would have Miguel and Greece. So 1 out of 15 would be our probability of getting Miguel, our bestie, and Greece, our favorite country. Okay, this will be the last example that we do. And this is going to be similar to one that you will have to do on digits. So please do this table with me. I know. Do this table with me in your notebook. It says a class ran 330 tiles of a 2-step action. And the action is toss the coin and then spin the spinner. Complete the table. So if we have counted this many of each of the events, the experimental probability here is 45 out of 330. We could probably simplify that, but I'm not going to. 59 out of 330, 64 out of 330, 45 out of 330, 58 out of 330, and 59 out of 330. Okay? So that means that those are our experimental probabilities. Now, if we did the expected count, we would be thinking about what we would expect if we split up 330 divided by 1, 2, 3, 4, 5, 6. Okay? So if I divide 330 divided by 6, I would have expected each of these to give me 55. Right? 55. Which means that the theoretical probability would be 55 out of 330 or 1 out of 6. Okay? Now, let's answer our question. For which compound event is the count the closest to the expected event? So looking at our count, the actual what happened in the experiment, which of those is going to be closest to our expected count, 55? Let's see. 59, that is just 4 away from 55. This is bigger. This is bigger. This is bigger. Ooh, 58 is just 3 from 55, and this one's 4. So which one is going to be the closest? It's going to be this outcome, tails and blue. We ended up getting that the closest to the expected count of 55. We got that 58. Okay, so that was just 3 away from the expected count. That was the closest. All right, at this point, you should be ready to work on digits 18.3 and 18.4. If you need help, raise your hand.